All right, I think I've showed this before. My power meter. Actually, this is the second one, though. I just picked this up off of eBay. I paid $11 for it, so I couldn't pass it up. So this is an instrument that I designed back when I was pretending to be an electrical engineer. I designed this back in around 1987, something like that. Anyway, it's a microwave power meter, and it has a 50 megahertz calibrator built in. It'll measure from minus 70 dBm to plus 20 dBm. It's very, very fast. We sold a lot of these to the Navy. We sold a lot of them to Motorola. And it's been a staple for a long time. Anyway, I don't think they build them anymore. But yeah, this one was listed as display didn't work. And I figured, well, since I was the designer of this box, maybe I can troubleshoot it. Anyway, I wanted the box because I wanted to do a teardown of it and show you some of the design parameters that I chose. What I did do, what I didn't do. The PCB configuration is of biggest interest because I've been doing a few videos on PCB design. And I'll kind of go through the thought process of how this was all laid out and why the PC boards are the way they are. Yeah, this is the front panel. It's been through the ringer. A lot of tape and stickers on the front. There were a couple models of this. There was the 8541, which is a single channel, the 8542, which is a dual channel. They were completely the same inside, except one had an extra connector on it. And we were hoping nobody bought that one because we kind of lost our shirt on that. We made more money on the price of the two-channel one. So, and you can either buy it where these are on the front panel or they're on the rear panel. And most of the eBay finds I've seen have these on the rear panel. They seem to be very often used in racks, and they just put them in the rear. It's got some LED configuration or status things on the front. This is a fairly more recent model than the one I worked on. It's had some software updates. It was originally designed at WaveTech, which is where I worked, and then they were bought out by Giga-tronics. I worked for Giga-tronics briefly and then didn't like them and I left. And while I was at WaveTech, we built a peak power meter. So it was this, we already had a peak power meter from the Pacific Measurement days. Trying to remember the part number of that one. It has an 18 in it. Anyway, this one was also a peak power meter, but it was just because of the sensor. We had a particular sensor that had a sample and hold in it. So the peak detection was done at the sensor, and then the meter could stay the same. But it had some units and some other things and configurations and stuff for whether it was peak average or peak detection burst. So there's some software additions that were added to this particular unit. That was probably done after I left the company. I can show you the back of this thing. It is heavy, actually, for its size. And so it has a GPIB control. This is the contrast for the front. I was wondering if the front, the display didn't work because the contrast was turned down all the way. So I have to try that out. I haven't powdered up yet. Still has the calibration sticker on it, so no one's been inside. Let's see here. So yeah, San Ramon is where Giga-tronics was. WaveTech was in Sunnyvale, California. Let's see here. This product has been, looking for a date. Tested. I don't see a date on it. I don't see a date. Unless that's 2011. It says 11 Giga-tronics on it, so I'm not sure. But if I remember right, you take these 3 screws out and the whole thing opens up. So yeah, let's do that. Oh, let me show you the bottom because it's all just holes. So we had ventilation coming in from the front, coming in from the bottom. It is a steel. I think it's why it's heavy. It's a steel box. Yeah, steel box. Okay. Woo. Sorry. Got my camera back here. It's not a good size. already did a video on the design of this thing, so maybe I'll put a link in down below on how this thing functions. I think I went through the schematic. All right, so it should come apart now. And why isn't it? Should pop out. Let's see here. Looks like it's been kind of jammed up here. Yeah, there we go. It's got some, I'll show it to you here when I pull this out. Oh, man. Well, these things are well constructed. All right, took the case off. It's got some nice RF grommeting around the crack there that keeps the RFI out. And does it look familiar? Yeah, it's gone through some revisions since I designed it. It has gone through some revisions. The covers for the analog sections are nicer. These used to be soldered down, and now they have removable caps. That's good. This is the calibrator. That looks like it's been the same. This is a really high precision 50 megahertz power calibrator. It's probably a 3999 there for voltage calibration. The most evident thing they've done since I've gone away is they've updated the transformer. I had an E-shape transformer, and they put in a toroid here, so that's a nice upgrade. Put in the toroid. It is a 68,000 base processor, nice big giant thing here. Everything's soldered down except for the ROMs and RAMs. And yeah, looks this board looks untouched. Looks like this board is exactly as I laid it out. And like I said, we'll do that. So there's two boards. There's a digital board, which is this. This is the microprocessor board, 68,000 and everything. And then on the other side here is all of the analog circuitry, okay? And there's some RF side and there's some analog input side. And it is split down the middle so that's analog digital. And there is a star ground that was critically chosen. So there's a star ground around this area here where all grounds come together and you have a truth here. In getting this thing to operate down to minus 70 dBm, which is I think 50 picowatts of noise, it's really, really important to separate the grounds. It took me a long time to get that working. And it all comes down to what do you tie these shields to? How do you separate the grounds? Yeah, it was a bit of a turmoil, but got that working. Yeah, looks pretty nice inside. This is a backup battery here that it's for memory. And that looks like it's tied down nicely. All right, 24 megahertz master clock. There's a expansion connector here that was added for possibly adding other things. I don't think that was ever used, but they've decided to still populate that with a connector, which is interesting. And the same over here, there's a connection here. Interesting. And I wonder if they've changed the GPIB controller. That one doesn't look familiar. Or maybe it's just a different part number. But this is the GPIB cable coming in here, and this is the transceivers and the control chip here. This is just a PIO chip there. And a couple more PIO chips over here. Yeah. All kinds of good stuff in there. I've added an LED. I don't remember if I had an LED on mine or not. I don't think I did. A test LED they can flash. It's nice to have an LED on your board, so when you're writing software, you could put in breakpoints in your software and flash that LED and know that you've progressed to a particular place, or have it flash a code or whatever. It's a nice troubleshooting aid. This is the calibrator cable here. It goes into this box here. I can show that to you. I think I want to power it up just to see if the display really is broken, or whether they just had the knob turned down all the way. It's a very, very standard two lines of 16 character display. I think anything off the shelf can go in there and be really easy to replace if it needed it. But I don't really need this thing working. I just kind of wanted to buy it because it was $11. And I thought you guys would get a kick out of it. We could go through this thing and see what's going on. Definitely has been some changes to the board. Probably due to component selection. Maybe some components became no longer available. There was a big multiplexer chip. All these analog signals had to be multiplexed in, and there was an A to D chip. So this might be the A to D chip. These might be some multiplexers or vice versa. I don't know, but they've changed that a little bit. Like I said, probably due to component availability. All right, let me find a power cord. All right, let's turn the power on here. The backlight works, and there's no display. Let me reach in behind and twiddle the contrast knob, and oh, nothing. All right, well, display is dead. And oh, I can see a little bit of display at fairly high angles. Yeah, it looks like there's nothing coming out the front at all, and none of the LEDs light up, which is a little weird too. So yeah, maybe it's a sick puppy. I don't know. Let me disconnect the battery, the memory backup, see if that helps it out. No, didn't help it out. So. Huh. Man. Oh well. We could check some of the all right, there's some test points here for the power supply, plus 15, minus 15. And ground, I guess, is the case. Let's turn it on. Plus 15 is fine, and Minus 15 is fine. 15, very good. There's an LED down here, a yellow LED. I don't know what that means. What is this? 7.1 volts. Don't know what that is. And here's a test point, DTAC, which is going to be operating. Let's see here. There's some test points down here. Here's a 5 volt. Oops, there we go. 4.7 volts, a little bit on the low side. A little bit on the low side. Got Nichicon caps, very nice. Oh, here's the ground down there. There's a ground test point down there. 4.7. Yeah, that's not very good. I don't think so. I don't think that's very good. Let's go to one of these. Yeah. Okay. 1.2 volts. Is that? All right. Well. I don't know if I can find schematics for this new version or not. I'll have to try. I've got a manual, of course, for the old one. But this has definitely been updated. See if I can find a schematic for this new version of PCB. There is, once we get it up and running, there's a whole bunch of test suites, at least there used to be, a whole bunch of test suites that I wrote, where you could go in and you could examine all sorts of, you could use this multiplexer to run around and look at the different voltages and try things out. And but let's talk about the PCB design, and I think that would be useful. All right, so one thing I want to talk about PCB design is that the PCB itself needs to be looked at mechanically. You have to figure out what is the size of the board, where are the locations of the connectors and stuff mechanically, and how can you do the board-to-board interconnect, how does the power supply wire in. There's all these things that you have to consider mechanically, and that will often set the dimensions of the PCB. All right, so you can see this PCB is basically, we have a particular width of instrument to work with, and so we're going to max out the length of the PC board in this direction so we can put on lots of circuitry. There is a front panel that runs on a connector, so that connector needs to be near the front, okay? And so you have two connectors here for the front, one for the display, one for the push buttons and everything. On the, we'll get to the analog section, but there's always also connectors for analog on the front, and those have to be on this side of the PCB, okay? The other thing is that there's a bunch of BNCs in the back that are used. Is this on, is this soldered? No, this is not soldered. So I can take this out. All right, so in the back, we have some BNCs that stick out the back, so that kind of sets the length. So this is just filling up the section, except you have a bunch of power supply over here, so you have to have a big notch here to leave room for the power supply. So that needs to be, thought of. How big is the power supply? How big is this notch going to be? And so a lot of times the mechanical engineer will actually give you the board dimension. Not the electrical engineer, but the mechanical engineer, the guy who has to package this thing up. So you can see the decisions we made here. We put the power supply over here. We have a notch. The actual power supply itself, though, is on this board. Here are the bypass capacitors and stuff. Here is a bridge rectifier. Here's a bridge rectifier. And then the power supply connects with this big connector here, which is kind of stiff. If I can get him out. Wow, he is stiff. There he goes. All right, so that's going to plug in here. So the power supply is here. There are 4 TO220 packages here, which are all the voltage regulators. The +5, the ±15, and then there's another one which I don't remember what it is, but there's 4 of them over there, and they are attached to the case, which is also acting as the heat sink, right? And so again, the power supply then has to go in a location where you can get access to the outer wall to do the heat sink. So that's good. So this particular board, we can take off these 2 front connectors. This one says LCD display, so it's labeled nicely. Let's see if this one. And this one is labeled front panel J2. Okay. Now, these have little pull things here. I'll show you when I get them out. I need to get this one out, which is kind of buried in there. Reach in and pull him. They're just a little plunger that you pull out, okay? And then this board should lift right out once we get those loose. All right, we have them loose. Oh, we need to disconnect all these as well. All right, so I've taken all these out, and now the board should just lift out. There we go. So you can see this is a pretty big board, and it makes connection to the bottom board with this one connector. All right, and so that's the connector here. So the biggest takeaway here is, if you notice, what's between the 2 boards? Well, this big piece of metal. So this big piece of metal, this is a really clever design that the mechanical engineer on this project did, was he had this piece of metal folded up, and it acts as the internal rigid backbone of the whole system. And it acts as a shield between the analog section and the digital section. So there's only one little hole here between the 2, which is right here where the star ground is, right? This is the go-between. And so it acts as a bunch of shielding. It also acts as, like I said, it's like the backbone of the whole system. It's attached to the front. And when you put the case on it, the screws basically push the case into the front. And so, yeah, it's a really, really, really clever design. But yeah, this is all of the digital section here. All right, and we can probably get a better look at it now and read maybe some part numbers back here. Let's see, where's my magnifier glass? I can't see anything without my magnifier these days. All right, found my magnifier. So back here we have a 5-volt regulator and another 5-volt regulator. So we have 2 separate 5-volt sections, a -15 and a +15. So I don't remember why we split the 5-volt. I should say why I split the 5-volt. I designed this stupid thing. Yeah, I don't remember what the configurations are here, but it has some things to configure it. Doesn't sound familiar. This looks like a It's either a real-time clock. It's a DS1231. I don't know if that's a real-time clock or a memory management, memory backup. I don't remember. There's another Dallas part here. 1210. Maybe that's the real-time clock. So there's a 1210 and a 12. What did I say? A 1231. It has some pretty big ROMs. It has 27C010, so they're 1 meg UV proms, version 408. Yeah, let me get some date codes on this thing. When was this thing produced? 97, 96, 97, 97, 97. Yeah, somewhere around the 97. This is 97. Yeah, somewhere around 1980. I mean, 1997, I should say. 1998. Board was probably built in 1988, something like that. All right. Again, here's the power supply section over here. They didn't solder those caps on very straight. This one's really leaning over to the side, so that's not very nice. Unless it blew out the bottom. Maybe that's... Oh, maybe that's what went wrong. Maybe the bottom of this capacitor blew out. And that's why it's not working. Let's take a look here. Let's take a look. Oh, yeah. Oh, yeah, it died. That one died. All right, Nichicon failed. 4700 microfarad at 16 volts. So maybe we'll fix that up and get it working again. Or do I care? Maybe I don't care. All right. Oh, here's the real-time clock. Yeah, see? My memory is not too faulty. There's a place for a crystal here, a 32.768 kilohertz crystal, and there's an unpopulated part here. So I remember there being a real-time clock. I just didn't get loaded in this one. I decided people didn't want those, I guess. I don't know. What else is there to say on PCB layout? Like I said, the power supply section needed to be laid out so that the regulators could touch the outside wall. These connectors needed to poke out the back of the instrument. You can see there's protection diodes on these things, so protect those external inputs. This is the contrast adjust for the LCD. A bit unfortunate it's way back here because it has to go all the way to the front. Let's see, this board was laid out with pads 2000. The original board was laid out with pads 2000. I know the designer. Yeah. What else is there to say on this board? 32-bit, 68,000. It's an HC68HC000-12, so 12 megahertz. And then there's some peripheral chips. 55 PIO, 2979. I mean 8279. I think that's the keyboard controller. Yeah. And another 55 over here. So parallel ports, right? All right. So here, I told you I would talk about these plungers here. They're kind of neat. They pop in, they expand. They're like a pop rivet, but plastic pop rivety thing. But you don't have to reach for a screwdriver. They just pop in, pop out. So we use those. Okay, now on this side of the board, these are the connectors that go to the sensors. And so we can disconnect those. And the sensors are pretty complicated. They have an E² prom on them with calibration data and stuff that you need to read out. So there's a path to do serial communication with the sensor. There's a chopping circuit in the sensor to remove any ground problems due to mismatches of metals and stuff. Anyway, lower the noise. There's a dual chopper where we chop in this direction, then chop in this direction, back and forth. All right, and then under here, which you can now open up. Before you couldn't open these up. I have a story about that, so let me tell you the story. So, if you're in the business of selling things where there's a competition, right? The competition always buys the competition, right? We were competing against Hewlett-Packard, so we would buy Hewlett-Packard instruments, and they would buy our instruments, and so and then they would tear them down. And these cans were soldered on. Well, when Hewlett-Packard placed their order, we knew where it was going. It was going to their R&D team, so they could reverse engineer it. And so we actually signed our names underneath the can before it got soldered down to the PC board. That was kind of fun. Anyway, let's see if we can't pop these. Can't pop these open here. A lot of things are signed. I remember the original Macintosh. If you opened up a Macintosh, I think the case, the mold that the case had everybody's names in it. There we go. Ah, there we go. See? It's very complicated inside. Lots and lots of stuff going on. And there are a bunch of FET switches for sure. And it looks like somebody's been in here. This is more complicated than the one that I designed. So they added some features to it. Not exactly sure what they added in, but basically it has a front-end amplifier, some filtering, some DACs where you could add in offsets. So there's a offset capability. You measure the offset and then you adjust it, make sure that you're centered around what you need to be centered around. There's a bunch of analog switching. There's a regulator in here, 7805 regulator also, so that's kind of interesting. Probably to lower the noise. Like I said, you're really fighting noise, and you might want to have a local supply. Yeah, so this is a FET switch. This is a DG409. This was all through hole, I think, when I designed it, and they've gone to mixed here. They some through hole and some surface mount. So, like I said, this has been redesigned. There's some linear tech amps up in the front. Some test points up at the front. Interesting. Yeah, somebody got a hold of this and put their mark on it. Very nice. Another DG, that looks like maybe it's a multiplexer, DG8430. This guy here. LTC 1410. I don't know what that is. And there's probably, yeah, this is the A to D. And so they have one A to D on both for each channel. Mine had a central A to D with a multiplexer between the two. So probably in order to speed the system up, they split it. And they have one A to D for this channel and one A to D for this channel. So they've put in an AD 7245. Yeah, so they have A to D here and A to D here. Not sure what that chip is, if it's a MUX or something, I don't know. And interesting, they've got a 7805 and a 7905, so they have plus or minus 5 volts running around in here. Again, like I said, probably a local supply to quiet things down. Yeah. All right, curious to look at the circuit and see what kind of improvements they made on my old design. Yeah, this is a decade later, right? 10 years had passed when this board. There's a copyright on it here in 1996. So the board was spun in 1996. So yeah, they've made some improvements. All right, so we need to talk about this because this is kind of the heart of the instrument. This is where the accuracy of the instrument comes from. It has local calibration. So when you use these power meters, you put the power meter on the connector on the front. That's the cal connector. And the cal connector comes over to this box. Well, this box is a power meter inside the power meter. So this is a thermistor-based power meter that's super, super accurate, but it just does not have very much dynamic range. And so you use this super accurate 0 dBm reference, and then you apply it to all the other ranges. Well, how do you apply it to all the other ranges? Well, you have a very precise step attenuator. Okay, so under this can is both the power meter inside the power meter and the step attenuator. And by having a power meter inside the power meter, that's how you get to the accuracy that this thing had, which was quite good. Yep, they didn't touch that a bit. Nobody's going to touch this thing. So what is this? Well, it's in this section. It's a 50 megahertz oscillator, okay? That's all this is a 50 megahertz oscillator. And the amount of power it outputs needs to be regulated, and it needs to be in a loop that holds it very, very constant. And that's what the LM399 out here is, a very, very stable voltage source that stabilizes this loop, that holds it constant. Now you have to figure out, well, hold it constant to what? Okay, so this is the power meter inside the power meter. You can see that funny little can there on a PC board. It's a Teflon PC board. And that is a thermistor-based power meter. And so that's what this is. So this is a thermistor-based power meter that gives you at least 1 decade of dynamic range, okay? Now, down here is the step attenuator. So this is the step attenuator that allows you to then transfer it up to or down to other ranges of the meter. So this is all PIN diode switching step attenuator stuff. Looks like some really, really nice pin diodes in there. They have gold leads on them and everything. And there's a thermistor in there as well. So it's thermally monitored as well. So there's a lot of things going on here, right? So yeah, this is in an oven, right? This is temperature oven. In fact, there's a little box that goes over here when you put this thing together. So this is heated up. So this is both a thermistor to do the measurements and a heating element to hold it constant. So this stays very, very accurate voltage base here, over here, and then you have a thermistor to monitor everything. So yeah, inside the power meter sensor itself is a thermistor, so you can monitor the temperature of the detection diodes on the front of the sensor, and so it keeps those accurate. Yeah, it's very, very complicated, and that's why you get the accuracy you get. So yeah, there's a peek inside.